All right, we're gonna go ahead and get started. We've got a packed day today. We want to give you as much time to work on your breakout group exercises as we can. So Amanda is going to go ahead and get started and take us through our last presentation of the week, which is building the case. To create these risk estimates, we need to provide good justification for them so that decision makers believe that we have the credibility to defend. So Amanda's going to walk us through how we can do that for all parts of the risk equation.
All right, so we've spent the week learning how to do a risk assessment, practicing elicitations, learning about the failure modes, learning about basics of all the disciplines, talked at length about how to do the calculations for the risk assessment, how to combine your failure modes yesterday. And so now we have all that information. If we don't do a good job of explaining it, we're going to have to start all over again. So we'll get set back to do more work. Good. All right. So by the end of this module, you'll be able to bind all that information together into a coherent argument about making the case for your risk assessment. You'll be able to figure out what the key evidence is, that you'll get how to figure out the key evidence to make that risk estimate, and then be able to describe sources of uncertainty in your risk estimates so that it makes sense to those key decision makers. And then finally, which is kind of the most important piece, is now that we've done the risk estimate and we've explained it, what do we recommend as the path forward so that the decision makers have something to work with and something to think about? All right, so what is the dam or levee safety case? So that's what we're trying to do here, right? Is make a case for how risky our project is. It's a logical set of arguments used to advocate a position that either safety-related action is justified or that no additional action is needed. So that's basically what we're trying to do. Is figure out, so in the core parlance, that's do we go to a higher level study or do we stay in what we call the routine program and just keep maintaining our projects? We use this case to present rationale in a formal and methodical manner so we can convince decision makers to take a responsible action. We use this along with the risk estimate in relation to those risk guidelines and tolerable risk guidelines that we have to support rational and consistent decisions, particularly across an entire portfolio of projects. We do that throughout our risk assessment. We start by documenting early on the background of our projects, all the way through to calculating the risk values at the end. So we really need to calculate or discuss the case for each component of the risk estimate. Now, I do have to apologize. I did not catch the change in terminology here. So the risk equation that Adam presented yesterday in his presentation at the end of the day is more current terminology, but so don't use this terminology, use that, or use what's in your book. But you have to make the case for the probability, explain why that's reasonable, the probability of failure given that loading, that hazard. So basically how your system is going to respond. And then finally the consequences, which we're really kind of the worst at in our work, as most of these engineers here, so, and geologists. We're the worst at explaining how our failures are going to affect the population. So why do we have to build a case? Well, risk is a number on a chart, but it's not just a number on a chart. We have to explain what that number on the chart means to support a recommended path forward, and explain to these decision makers who weren't involved in your risk assessment, they're only seeing what you tell them, why you think we should do what we should do. These guys are making major decisions about lots of projects, and this could cost lots of money potentially in the future. So you really need to have a concise argument to explain it to them. So first, we'll talk about building the case for the annual probability of failure. So the easiest way to do this is make sure you have a good set of more or less likely factors to walk through the key points that you felt affected how the dam or levee was going to fail, one way or the other. So you can highlight that on the more or less likely factors for each node. You can highlight ones that were key to you making the decision that you did and you estimating your probability of failure the way you did. So if you have a really high likelihood of failure, you're probably going to have either a lot more likely factors or some very key more likely factors that overrode everything else in your risk estimate. And you need to point that out. The next thing, and this is kind of my favorite that we've started going to in recent years, is taking an event tree, which walks you through step by step by step, the probability of, or the PFM, and adding in key factors onto each node. You can explain why you thought this node was more or less likely to occur. And so in the end, you'll get to a figure like this, and those decision makers have that as kind of a roadmap to walk them through what you were thinking. One of the things to remember when you're doing your explaining of things, a lot of times you'll have a model to walk through, or to help you estimate your probabilities of failure. You'll have toolboxes, a stability model, maybe a screen level structural model, or structural toolbox, something like that, to help walk you through and give you an idea of how the project's going to behave. Well, some of the things to remember on that is, this is one of my favorite quotes. I bet y'all have heard it before. All models are wrong, but some are useful. So you need to explain and understand the limitations of your models. You'll have input that's required from a multidisciplinary team. Make sure everybody's on the same page about what the assumptions are, what the inputs are, and how reasonable they are. They're not going to be 100% accurate. Sorry to the structural engineers in the room, but they will be reasonable in most cases. Structural engineers completely ignored me, so I'm glad you're paying attention. So often there's a key feature that will control the results in your model, and you need to kind of understand how that affects things. So I'm a geotech, so I put in that weak layer and stability analysis will often control your entire model. Doesn't matter what the rest of your model's doing, realistically. If that weak layer is there and if it's continuous, it's going to be the controlling layer in your model. Another problem or concern to think about is that a model often only addresses one node in your event tree. So you have a whole rest of the event tree that you have to understand and figure out how that fits around your model. Sensitivity analyses are key. You can't really understand a project unless you've done some sort of sensitivity analysis or parametric study or however you want to call it. But make sure you have a good understanding of how, if you don't, at least in geotech, you're never going to know the answer 100%. You're going to have a range of values for your material properties. So make sure that you understand how those affect your results. So assigning a likelihood of initiation or progression or likelihood of failure, wherever that model fits on the event tree, takes judgment and interpretation of those model results and how reasonable they are for your project and for your structure. All right, so now that you've gone through, you've built the event tree, you've explained your model results, you understand how they fit into the risk assessments, tell the reviewer, the decision maker, what they should be thinking. Explain your critical loads. What were you thinking with your critical loads, particularly for an SQRA? QRA, you're going to do estimates on a load by load basis, but in SQRA, you often have one critical load that drove your risk estimate. Tell them what that is. Don't let them guess. Don't make them guess. Don't make them look it up. That's a problem I've seen in PAs. I'm like, I don't know what the critical load is. Tell me what it is so that I don't have to go looking. Find the failure progression and pathway. Tell them how it's going to happen, where you think it went. Draw pictures. Pictures are awesome. Use the event tree outline and walk through the risk estimate for them. Explicitly state the key factors. Say, this is what drove us to believe the risk was high or the risk was low. Maybe one node and maybe all the nodes, but tell them that. Don't leave them guessing. Highlight any background information that was important. Document any assumptions that you have in your risk estimate. And then we'll talk a little bit more uncertainty later, but that'll be documented separately from your risk estimate. Write that down somewhere so that you can list it out later and highlight areas of uncertainty. And then do a check. Does it make sense? Does that seem reasonable to you? Check it against case histories. Check it against those databases. I think Matt mentioned the database of internal erosion values and stuff like that, about historic failures. So in your rationale, emphasize the proper nodes. If you have a high system response probability, you may need to discuss what part of every node led to a high probability of recurrence. If you have a low system response probability, where there are key nodes that drove the risk estimate down, because usually it's a few key nodes. So like in concentrated leak erosion, you have a filter on your dam. That's going to nearly eliminate the possibility of sealing. So talk about that, highlight that, show them why it's a useful feature of the dam. So here's an example of a low probability of failure description. So probability of failure due to BEP is low because of a filtered exit through the incline drain. So we've got a filtered exit here coming up, and the likelihood of BEP is pretty low at that point. So the evidence, you have to give them the evidence. Filter criteria is met. Show a picture of you comparing the filter criteria. How many tests were there to help you understand that you have a good evaluation of the foundation conditions and the filter conditions. Filter material doesn't segregate easily. Construction control procedures were excellent. Show either evidence of that or specifications, something like that. Put it on the event tree too. That's another good way to do it. So walk through each node. So that this is just an example of what that would look like on an event tree. And then a description of how you might make the case. You can turn this from a bulleted list into a paragraph rationale. High probability of failure. So probability of eye wall instability and failure as a result of overtopping is high. So they've done an analysis that says that landside scour depth greater than 2 feet, or will be greater than 2 feet following thermal overtopping. They've got case studies to suggest that that's a problem. And they've done a CI wall model that indicates walls unstable once that scour depth gets that deep. So they walk through that and put that into this event tree. There's fewer nodes, but each of these nodes leads to a high probability of failure. And again, here's a bulleted list that you might come up with during an SQRA session or QRA session. I think SQRA is common, so that's why I'm thinking SQRA. And you can turn this into a rationale paragraph in your report. So that's risk driving failure modes. So we're getting a lot better, slowly better at making a case for risk driving failure modes. We do a lot of background discussion, a lot of more and less likely factors, helps us make our way through that case. The one thing that we're starting to work on more is making the case for excluded potential failure modes and having the rationale there so that somebody in the future can come back and say, this is what they were thinking, this is why it's excludable. So one of the things is a lot of times we're able to exclude something at this point in time due to infrequent loading. So occasionally we're able to exclude overtopping because of that. So, however, as you all know, elevations, loading change year by year by year, right? So every time you do a updated H&H analysis with most current methodologies, something's going to change. Might go up, probably go up, it might go down if you're lucky, but probably go up. So one of the things you want to do in your excluded rationale is give the future team something to think about of if the loading increases, what is there that could help you further exclude it? So talk about the physical processes that lead to either, oh crap, if we do have an increased loading, it could be a problem, or if we do have increased loading, it's still not a problem because the physical process isn't there. All right, so that kind of gets you to the loading, or through the loading to the probability of failures. The case for the loading, I don't talk about as much here because that comes down to describing what analyses were done to develop your hazard. And that is, we have several courses related to loading conditions for hydrologic hazard. We have less available to us for seismic hazard, but we have good toolboxes from USGS help us with that. So if you do that modeling and you properly document it, that is what you need to document your hazards. So those are different classes on proper modeling documentation. So consequences. Consequences is one we kind of were like, okay, we got all the way through the APF, we're good. Crap, what happens if the dam fails or levee fails? We always tend to kind of forget that. And part of the problem is that the lower level risk assessments, the consequences are developed ahead of time, and we often don't have the modeler in the room to help explain what went into their model. So it does tend to be kind of difficult. We still have to do it. So life loss consequences. The case for these consequences requires the same standard of care to describe as the failure probability. So with life loss, talk about how many people are exposed to flooding, you know where they're at, talk about where they're at, and where, you know, if it's industrial or residential, what's the structure inventory that you use, is it reasonable or is it old? How does evacuation occur? We don't usually model evacuation at lower level risk assessments, but you can talk about what that might look like. Is high ground nearby? Are there bridges that they have to cross that might get cut off? You know, what does that look like? Talk about it qualitatively. So how severe is the flooding? So what does that mean? That means how fast and how deep is that water gonna kind of come up on the population? Are people in these structures that can withstand flooding? So what kind of structures do you have? Is it reasonable that they might survive a flood in those structures? And then talk about why the likelihood of life loss is what it is compared to the population at risk. You know, look at the percentage of life loss of population at risk. And then qualitatively talk about indirect life loss. I think Nick talked a little bit about indirect life loss in the consequences discussion on Tuesday, but we do want to at least touch on it and say, hey, this is a concern or not a concern depending on our project. But some projects could be a very big deal. So here's just an example of life loss rationale. They compared the modeling scenario that they had to the potential failure mode that they're evaluating. They talked about any model assumptions in here. They talked about the downstream community and what the downstream community looks like. In a lot of cases, you won't have consequences, elicitation, like Nick talked about, going out and talking to the local EMAs. But your operations team, your emergency management team will often have knowledge of the downstream communities that can support this risk estimate and this consequence estimate. They know the local people. They know how things work. So talk to them. And then how bad the flood is. So I'm talking depth and velocities in your in downstream population areas. All right, so I mentioned that uncertainty is a whole separate discussion. So in quantitative risk assessments, we estimate uncertainty and we plot it as part of that cloud of numbers that you guys saw. In SQRA, we don't do that. We have an estimate of the mean risk, that's that box plot, and then we just describe our uncertainties and we kind of just list them out and discuss how they might affect the risk estimate. So why do we try to quantify the uncertainty? Well, it helps the risk estimate team evaluate the problem more thoroughly and anticipate what to change. It helps decision makers understand what we don't know and why we don't know it. And is it something that we can find easily, something that would be difficult? How would it affect the risk estimates? And that will help us decide if additional studies are useful or data gathering is useful. Investigations, anything like that. Well, it helps make the case for additional work if we need to do additional work. So I believe this was a quote by Greg Scott. This is a paper written by Greg Scott, Nate Snortland, and Carl Dice, all former, officially now former RMC folks, leaders. And they have a good paper here about risk analysis in the dam safety case. And this quote right here kind of stuck out. So it's presumptuous to believe that we are capable of obtaining a single precise number that truly represents risk. So the risk number estimate is important, and it's an accurate representation of our understanding of the risk of the project. But we need to be humble enough to understand our limitations and admit what we know we do not know, and try to figure out those uncertainties. So what? For each uncertainty present in the risk analysis, provide the so what. How could this uncertainty affect your risk in this other likelihood or the consequences category? And could it result in a change in the dam or levee safety case and recommendation? If you found out a key piece of information, could it affect what you recommend doing for your project? Okay, so then the final step, once you've made the case for your risk, once you've quantified your answer or listed out your uncertainties, discuss your uncertainties, recommend a path forward. So possible risk outcomes. Okay, you can take action to reduce the risk. Like it's high risk, we need to go out and do something. The risk is kind of marginal. We're not 100% sure. We need to do further studies to reduce the uncertainties in our risk, help us understand the path forward. Or best case scenario, we don't need to take action. The dam or levee is low risk, it's tolerable, and we can continue maintaining it. We're not going to just ignore it. We're going to put it back into routine maintenance and O&M. Those are kind of the possible actions. These have different names for different agencies. These in the core, these have different names for different types of structures, but these are the general path forward. When we are confident that the risks plot above the average annual life loss guidelines, we've got risks that are up here well above what we consider a societal tolerable risk. That risk justifies some sort of risk reduction activities. Consideration of uncertainty. So this is a quantitative risk assessment. So we've quantified our uncertainties. And we're still saying, yeah, our uncertainties aren't going to reducing uncertainty is not going to change the decision. We still need to perform some sort of risk reduction activities. And in this case, this is actually pretty low uncertainty. We could have orders more magnitude of uncertainty, usually due to the hazard. Sorry to the H&H folks. So we're gonna go forward with some sort of risk reduction activities or actions. So these are some arguments that can be made that you should evaluate for further study. Estimated risk justifies some sort of risk reduction activities, but there's quite a bit of uncertainty. So you should probably do some more investigations to try to reduce that uncertainty to see if that can change the mean risk estimate. And if that moving that mean risk estimate changes the justification and changes the recommended path forward, then you should probably do it. Finally, taking no action. So the risk generally plots below guidelines. You have a really low uncertainty, and there's really nothing else you can do that you need to do to make the case that this is good. It falls underneath the expected annual life loss guideline, not the average annual life loss guideline. Sorry about that. So this is a good example of where we would say, nope, we're good. Let's continue maintaining our facility. So I'm just going to leave you with this other quote. Greg Scott is, if you've never met Greg, he's really awesome. He knows his stuff when it comes to risk analysis. And he has all the good quotes. So. Any questions?